that is being hidden. And we have a sensor. Typically, it's going to be a camera for the stuff we're talking about. And what it's doing is it's taking some measurements. It's measuring like our raw detections that we were doing before. And we're going to refer to those as noisy observations of whatever the underlying state actually was. The system that we're assuming is that at every time step t, the state, the underlying state changes from x of t minus 1 to x of t. So here we have x of t minus 1 to x of t. And then at time t, we get a new observation. We get a new measurement. And our goal, your mission, should you choose to accept it, is to recover the most likely state time t. Now, I was thinking about that. It's actually, that's not quite right. What you want to do is you really want to estimate, not the most likely state, I'm going to cross that out and say the distribution or density. So if I have the density, that is, I have some belief about where x might be, I can tell you the most likely place, that would be the highest probability. I can tell you the average guess, that would be the expected value. But the idea is that we're going to have a density. And so your goal is to recover or estimate this distribution given, first of all, everything you've seen so far, right? So you've been taking measurements all along since last Tuesday. Where is this thing now? And the other thing that was given to you was some knowledge or some model of the state dynamics. That is how this thing moves. Now, you may have to estimate some of the parameters, but you may know that, I'm going to assume that this thing has a particular velocity and the acceleration is just some noise. That would be a model that you're going to assume is known.
So what do we exactly mean by state and measurement? Let's try to understand with an example. Say you're looking at a pendulum, swinging back and forth, and assume that it has a marker on it that you can detect reliably using one of the corner finding or template-based matching techniques you've learned so far. Now we can identify different quantities to describe this system. For instance, the center of the target can be located using an x and y coordinate. Similarly, the pendulum rod has a certain length. Let's call this L. The circular weight at the end has a radius r. We could even say that the pendulum makes an angle with the vertical line. Let's call this theta. When defining a model for this system, which of these quantities would you include in its state, and which quantities are directly observable from images? That is, part of the measurement model. Again, the quantities we are looking at are the xy location of the target, the length of the pendulum L, the radius of the circular weight r, and the angle made with the vertical theta. Mark the appropriate checkboxes. If you think about it, the only thing that we can directly observe is the xy coordinate of the target. Yes, we could try to detect the pendulum rod or other components, but that may not be as reliable. So this is the only thing that needs to be in our measurement model. The same xy location can serve as our system state. However, since the motion of the pendulum is constrained by the fixed length rod, assuming it is fixed length, it's better to compress the state. It really only has one state variable, that is theta. Again, this is assuming that L and R are constants. When analyzing a dynamic system, it is very important to identify what are its real degrees of freedom. Sometimes the state variables you need to keep track of may not be immediately apparent. We will see examples of such systems later on.
So to give you, again, still a little bit intuition, but getting a little more formal. So here we have that same person walking at time t, and then there's a question of what do we do at time t plus 1. And the idea is that from time t, we have some prediction or some belief that's indicated here in red of where we think the person is. Okay, and that's our prior. So before we take any measurements at time t plus 1, this is our belief. By the way, I will go back and forth. The slides sometimes go back and forth between whether we're talking about moving between t minus 1 and t or t and t plus 1. It doesn't matter. It's just going from one step to the next, and sometimes I screw up one way, sometimes I screw up another way. This is like the story of my life. All right, so at red we have, the idea is we have some prediction at time t, and we want to know what's happening at t plus 1. At time t plus 1, we take a measurement. That's what's shown here in green. Okay, so we had some distribution that was our belief about what's there, and now we have some measurement. Now notice that this measurement is also a distribution. We're going to talk in a little bit about what that means. It means two different things. One you can think of is that given that the person is someplace, how likely would be the current measurement that I got? So you see here, let's assume the measurement was there, okay? This distribution says not how likely is the person at a particular place. That's what I'm trying to estimate. What this distribution says is how likely would this measurement be, how likely would I be to get this measurement if the person was at these different locations? That's a little confusing. When we do the math of likelihood, that'll become clearer. For now, you can think of a measurement that's just a little bit noisy. I don't know, it gives me some bounds on where the person probably is. And then finally, taking that prior belief or prediction and the measurement, I come up with what's referred to as either a corrected prediction, final estimate, or the technical term is the posterior distribution as to where I think it is. And that's what's shown in blue. So I go from a prior or an old belief to a measurement to a new belief. Writing these out as equations, so the prediction can be thought of as this way. What is the next predicted state of the object? Here I'm back to x of t given t minus 1, given all the previous measurements, okay? So you see here that it says given y from 0 to t minus 1, so those are all my measurements up until before t, make a prediction at time t. Correction is, again, I want a distribution. Remember, I'm coming up with a probability distribution of xt. Given what's new, well, what's new is I have my new measurement, okay? So basically, this was my prediction based upon my measurements up until t. Then when I'm done, I should have a prediction including the current measurement. So basically, the tracking is this propagating what's called, as I said, the posterior distribution, posterior density of state given the measurements. So this term here, this is my posterior because it's after I've taken the measurement at time t.
Wait a second. Why do we need probabilities? I guess it makes sense for prediction, because we don't know what the value of x is at time t, since we only have information till time t minus 1. But what about correction? We know what the measurement is at time t. Why can we not get a definitive value for xt? Why is this a probability distribution? Is it because the state and measurement are different quantities? Like in our pendulum example, where we said the state could be just the angle theta, and the observation was the location of the target. Or could it be that observation values are unreliable due to underlying sensor noise or even imperfect detection algorithms? What if observations are missing or beyond known limits? Is that a good reason to model state as a probability distribution? Let's think about the first point. Our pendulum example is one where x and y are different quantities. However, this is not a strong argument. Here our state can be precisely computed using the observation. It is merely a more efficient representation. However, there are other cases where the difference between state and measurement is more important. You're looking at a clown juggling 3 identical balls that you want to track. You have an excellent detector that, given any video frame, spits out 3 xy coordinates that are the centers of the 3 balls. This is your raw observation, x1, y1, x2, y2, and x3, y3. There is no guarantee that x1, y1 refers to the same ball across frames. Clearly, you need something more in your state model. How about velocity, including direction and magnitude? That would help you predict better which xy belong to which ball in each frame. There are many other situations like this where directly observable quantities do not suffice as the system state. Therefore, the first point is valid. More importantly, you need to realize that detection techniques, especially dealing with real-world data, are not always 100% accurate. Noise can be introduced into observations due to various reasons. Sometimes just the discrete nature of digital images results in observations that are not smooth. It is best to take observations with a grain of salt. Remember the video where that guy walked behind the pillar? That's a missing observation. If you didn't have anything more in your state, where would you say the person was? Well, you could say that it is highly likely that the person is nearby where they were last seen. Therefore, the last point is also a valid reason for modeling these as probability distributions.
To do this, we're going to make some simplifying assumptions. The first assumption is a Markovian assumption, and that's that only the immediate past matters. So what this says is, if I know all of the states up through t minus 1, and I want a prediction of the state at time t, that just depends on the state at t minus 1. Now, these are x's, not the y's. These are if I actually knew the state. What this tells me is, if I wanted to predict the state on Wednesday, and I knew the state on Tuesday, Monday, Sunday, Saturday, it's all the same as knowing the state on Tuesday. Okay? I only have to know one prior state. Now, some of you might ask, but wait a minute, if I know Monday and Tuesday, I might be able to estimate the velocity for Wednesday.
If I know Monday and Tuesday, I might be able to estimate the velocity on Wednesday.
So that's right, except not, because your state can also include the velocity, right? So if I knew the position and the velocity on Tuesday, I make a prediction about Wednesday. So this is the Markovian assumption. This probability of xt given xt minus 1, that's what we refer to as the dynamics model. That's how things are changing. Second simplifying assumption, we're going to assume that the measurements, the probability of the measurements, remember these are noisy measurements, given everything in the past and the current state, only depends on the current state. So this is where we say that the probability of a measurement given a particular state and everything else only depends upon the state. By the way, this is called the observation model, and I will tell you it is this particular assumption that is sometimes the most suspect. One way you can think about this, suppose you have some noise in your sensor that is related to some other processes going on, and it changes in a particular way that you might be able to estimate. This thing says, well, I don't look at my previous measurements in order to make that prediction. So for everything we're going to do, we're going to make use of this observation model where the likelihood of the measurement depends only on the current state. Just know that for more advanced things like conditional random fields and other approaches, we're actually able to make the current measurement tied to previous measurements. But we're not going to do that here. I know some of you have taken various machine learning courses and you're familiar with graphical models. And if I were to draw up this set of simplifying assumptions as a graphical model, it would look like this. And what this says is that some state x depends only on the state at time t, depends only on the state at time t minus 1. And furthermore, it says that my measurement depends only on the state. And whenever I look at that, I always think to myself, okay, that's a joke. Why? Because those of you who know what this is a hidden Markov model, an HMM. See, now Megan, who was helping me with the slides, she didn't know that, so she didn't know how funny that was. So she's now, what is it, ROTL? No, ROTFL, sorry, I left out the floor. It's really hard to say emoticon things. Not emoticon, what do you call those things? Whatever they are. Now she's getting up. Another way of thinking of this is that tracking is just an induction process, right? Induction, like from math, is if I know how to do n, then I know how to do n plus 1. When you show what the sum of a geometric series is or things like that, you tend to prove these things by induction or something like that. So for induction, you have to have a starting case, a base case, so you have some guess as to how things start. Maybe for our tracking, we have some distribution. It could be a very uncertain distribution. And then with that first frame, we take a measurement, y0, and then we would correct our estimate. And then we just keep iterating through this, right? So at every time t, we make a prediction for time t plus 1, take a measurement, and we correct for time t plus 1. And somebody spent a lot of time designing these beautiful arrows, so I wanted to make sure you saw them too. And if you go take a look all over the internet, you'll find these arrows. So now let's look at these steps one at a time. Let's first look at the prediction step, okay? So our prediction step is, given some belief about at t minus 1, and given the measurements all the way up through t minus 1, make a prediction of xt, state at time t.